Okay, so this is a good Lenz's law problem. So I've got this loop and I'm bringing in this magnet. What's that going to do? What kind of current is that going to create? Let's kind of talk through this one. So let me start my video, stop sharing. I've got my magnet here. Here's a north and a south. I've got this loop, and we're told which direction they want us to call positive is if the current goes around like this, coming out towards our face, we want to call that positive. Okay, so as I'm bringing this in, we're coming in like this. We could calculate the flux that's passing through here as a function of time. We could use Faraday's law and calculate the change in flux, the rate of change, the derivative of flux per unit time, and calculate our voltage, our induced EMF. And then from there, calculate our current, just using V equals IR. Or we could use Lenz's law that says, look, whatever you're trying to do, this guy's going to create a magnet to try to stop you from doing that. So I'm trying to squish these two together. Lenz's law says, I don't like you doing that. I'm going to create a little tiny magnet, not as big as what you're pushing, but I'm going to create a little magnet that tries to stop you from coming toward me. Okay, so remember, thumb points in the direction of the North Pole. Your fingers will curl in the direction of the induced current. So my induced current, as I'm pulling these together like this, I'm bringing this magnet in. This little magnet says, I'm going to try to stop you. He's going to create an induced current that flows around like this, the opposite of what I drew there. So that's going to be a negative current to begin with, because the directions told us that's positive. And as I get closer, that's going to get bigger and bigger in the sense of more negative, because my flux is getting bigger. More and more of these magnetic field lines will be flowing through my loop here. So my flux is getting bigger and bigger. The further away I am, the smaller the flux. Okay, what about once I get all the way through? Now I'm leaving. So now I'm over on this side. Maybe I'm halfway through, 3/4 of the way through. I'm trying to flow away. I'm trying to pull this magnet away from that loop. Well, this loop says, I want to stop you from doing whatever it is you're doing. You're trying to pull away. I want to try to hold you back. So I'm going to create a little magnet here that has a north to try to attract the south end. So that's going to create a current that flows like this. Wait, which way did I draw this one backwards? Now I got to redraw it. What did I have before? I had a north-south. I think I may have gotten my sign backwards here. This guy's going to create a south-north to try to stop me. Yeah, that's going to flow around like this. Let me pause a second. Okay, yeah, I got it now. So when we're trying to bring this magnet in, the first part, I had this backwards. This guy creates a little magnet to try to stop me doing what I'm doing. That's going to create a magnetic field that points to the left. Thumb points in the direction of north, which will flow around like this, the same way I had positive. So we do start off positive because we're flowing around like this. Then on the other side, when the magnet is trying to leave, this guy is not going to try to stop him from coming in. He's trying to stop him from leaving. So he creates a north on this side on the right to try to hang on to that south. Thumb points in the direction of north. My fingers curl around in the direction of the induced current. That will flow around like this, the opposite of what they told us was north or positive, so negative. So that's this one. And we can see here, that's the correct answer. Okay, similar question there. Here you got to be careful. I created a video for this one. This is one of the ones I'm talking about. You got to be careful. Did they give you the correct angle or not? So they tell us some angle theta here. That's the angle between B and N. The vector perpendicular to A. That's the angle we want. That's the correct angle. Sometimes they're going to give us the wrong angle on purpose. So you'll have other problems. I think there's even one in the homework where you'll have some surface maybe, and then I'll have B pointing up like this, and they'll give me this angle here. Maybe they'll say that's 20 degrees. That's not the angle I want. In flux equals B a cosine of phi, I want this angle, the angle between B and perpendicular to the surface, not the angle between B and parallel with the surface. Okay. That one we're just calculating. Everything is perpendicular here. This one should be relatively easy. Okay, we have a B that's decreasing with time, points out of the board out towards our face. We want to figure out which direction the current's going to flow. So again, we could do this in terms of Faraday's law and think about the direction in which the flux is increasing, and then the induced current will be in the opposite direction. So I'm going to do this and make it really hard. And then I'm going to do it the easy way. Let me reread the question just to make sure I'm doing it correctly. B is decreasing with time, yes. Okay, so there are my B's, and B is decreasing. Here's my loop of wire. So Faraday's law says figure out which direction the flux is increasing in. So my flux is right now pointing out. I've got B pointing out. So B is flowing through this loop. But B is decreasing with time. So my flux is increasing in the opposite direction, in the downward direction. So this is kind of weird. You got to think, if we call up positive, so at this moment, flux is a positive number, just B times A, right? But it's because B is decreasing, flux is getting smaller and smaller. So my flux is going like it's starting at some maximum positive and it's getting smaller. So my flux is increasing in the negative direction. Decreasing positive is the same as increasing negative. Faraday's law says in whichever direction your flux is increasing, your induced current will point the opposite way. So my EMF will create a B, a new B, that goes opposite of the increasing flux, which will be up. So if B points up, induced B points up, my current would flow around counterclockwise. That's thinking in terms of increasing flux, and it's going to burn up your brain. It's much easier to think Lenz's law literally kind of says the same thing. But whatever it is you're changing here, the induced B tries to stop you from doing that. It does the opposite. So what's going on right now is I have some ups, right? But B is decreasing. That's equivalent to losing ups. So some of these ups are disappearing. Well, the induced current says, hey, you just changed something. I want to stop you from changing that. I'm going to put back some of that stuff you lost. If this were a super magnet, this material here, if it were super magnetic, it would perfectly balance out whatever change you were making. It would perfectly balance it out. If we lost 3 ups, we would get back 3 ups. If this is not a super magnet, though, it doesn't quite make up for whatever it is you lost. If I lost 3 ups, I might only gain back 1. And this is all analogy, but you get the point. So I'm losing ups. The induced current is going to create a magnetic field to make up for what I lost, try to stop me changing what I'm changing. That B points up. My induced current then, right-hand rule, will flow around counterclockwise. These are good problems. Like here, this guy's moving away. We want to think about, am I sharing? Yeah. What kind of flux is passing through here? And then as I'm changing that, what's happening to that flux? Is it getting bigger or smaller? Which direction is it increasing in? Or what am I gaining or losing? Lenz's law says whatever you're gaining or losing, I'm going to create the opposite of that. I'm going to give back what I lost, or I'm going to take away what I'm gaining. Same thing here. I don't want to do all these for you. That one has a written example. This one, I just kind of warned you about. Hint, hint. And then these questions are the ones that use, these are those bar problems. You're going to be using this formula to find your induced EMF. That's your voltage. Little v here stands for velocity. That's how fast we're moving the bar. That's right there. Excuse me, right there. There's the length of the bar. There's L. There's B. Literally just multiply the numbers together. To find the current, just Ohm's law, V equals IR. Remember, EMF is not a force. It's called electromotive force because some dumb people named it. They didn't understand. They didn't even really know what forces were, much less understand electricity. So when they named this thing EMF, it was a terrible name. I really wish we'd stop using it. That stands for electromotive force, but it's not a force. It's a voltage. So we really should just call that capital V. And then V equals IR to find I. Exact same game here. Be careful with your, whether or not you got the right angle there. And then more Lenz's law problems. This guy here, I think I did some of these in that other video. That's an eyeball. I know that looks like a housefly, but it's not. That's an eyeball looking down. And from that guy's perspective, this would be, let's see, that I think going around like this would be counterclockwise, and this would be clockwise. Okay, a lot of good questions in here. I like all these. Any of these could end up on your test. All right, I think that's a good place to stop.